materials around us, or something like that. Okay. So generally it's like works like this. So around us there's usually, if you count, there are always radiations around 30 to 34 counts per second. That's how it works. All right. Now, so now let's now continue with this. So last time, basically these radiations are detected, which are like microwaves, right? So I just want to, want you guys to write a small note, and then we'll move forward to the last chapter that we have. It's basically, you need to remember that CMB radiation is very uniform. And has the exact profile expected to be emitted from a hot body that has cooled down over time. In fact, over a very long time. All right. Now, what CMB implies, basically what you need to understand is that this implies, because wherever you go, you get the same result, right? From all directions. So it means that implies that all objects in the universe are more or less uniformly spread out like that. Okay. Now, the important thing that we're going to do today, write this, is basically measuring galactic speed and distance. So, second please. So first of all, what you guys need to remember is that the difference, let me write it simply here. The difference between the actual wavelength and expected wavelength divided by the actual wavelength equals to the speed of galaxy divided by the speed of light. To remember it like simply, you can remember this change in wavelength that you see after a while over the wavelength that you're basically wavelength of particular light that is coming towards you equals to the speed of that galaxy and the speed of light. This will give you how the galaxy, what is the speed of galaxy when it is moving away from Earth. All right, that happens, distant objects, that how they are basically receding away from Earth. All right. Now, this method is basically of using redshift, right? Because redshift basically tells us when the wavelength has changed, when it has moved away from us. This is an apparent change. All right. Now, the other thing is when you're measuring distance using supernovae. Now, I just want to tell you, so there are certain things which are called standard candles, okay? And basically we can say that this one of the key methods is to use standard candles. In A levels, you will basically study about them in bit more details, and these includes supernova. All right, or novae. Novae is the plural form. So what exactly is the supernova? If you want to, define supernova, supernova can be said that basically they are exploding stars, in short, and when they explode, basically they are so bright that they can be seen clearly even though they might exist deep into their parent galaxy, right? Now, the light that shines, right? So we can make calculations. Again, the rest of the part is in A levels. That this allows basically the distance of the galaxy to be calculated. That's just a short thing that I wanted to tell you. All right. Now, then we have Hubble's law, and the Hubble law is defined as the recessional. Recession means when something is going away from us, right? So recessional velocity v of a galaxy, that's the same v we studied like here. Galaxy is proportional to the distance from Earth, right? Now, so Hubble was a scientist named Edwin Hubble. He basically studied many galaxies, many galaxies, and he just plotted them over a certain graph, right? So basically the graph seems like this. Let me just show you. So on the graph, he actually plotted all these. So here it is the recessional velocity v, and on this side we have the distance from us, distance d. And when he did it, he was like many galaxies he studied and plotted it. What he realized was that basically the speed at which they're receding away from us is directly proportional to the distance from us, which basically means that if you're looking at a certain galaxy right here, so its speed is basically, if it has a higher speed, then it will be more far away from us. If you're looking at a closer galaxy, it will have less speed and less distance from us, like that. Okay. Now, so what he did was he presented the formula that the Hubble constant, which can be found out by the gradient of the graph, is equal to v over d, where this is the recessional speed or velocity, and that's the distance from us. Is that clear, everyone? Any questions here? Please let me know.
Sir, your screen on your YouTube stream is not showing.
Really? Wait. Which screen? My recording screen?
On the YouTube stream.
Oh, damn. That's not fair. All that exercise to nothing. Sorry. I probably, there's a mistake I made. Sorry. Wait a second. I need to fix that. All right. It will be fixed now. Sorry. So basically the recession, if you guys have any questions, please let me know here. Okay. So what he says is, he says that two things actually. All right. Number one, that the galaxy further away from us, the further the galaxy, the further the galaxy is away from us, the greater the distance, the greater the speed, velocity it will have. All right, so you guys need to remember that. Now, thanks to Hubble, now we are able to calculate the speed, the age of the universe. All right, and you just need to remember this, that age of the universe. Please note here. All right. So if we use 1 upon the Hubble constant, this is, by the way, the Hubble constant, we can estimate the age of universe. Okay. Currently, this is just a fact. Currently, our estimate is 37.5 billion years ago. We believe Big Bang happened. So that's when, the universe began. and you can use it. The Hubble constant, you don't need to remember the value, they will give you themselves. Okay. Now let's do one question and be done with our course. So it says a distant galaxy is 20 light years away from Earth. Use Hubble law to determine velocity of galaxy as it moves away from Earth. All right. They've said the Hubble constant is 2.2 times 10 raised to minus 18 second minus 1, right? Now let's try and do this. First of all, the distance that we have is 20 light years, so we got to change that. All right. Now how do we convert 20 light years? We got to remember this, that 1 light year is equal to 9.5 times 10 raised to power 15 meters. So 20 light years is going to be 20 times 9.5 times 10 raised to 15 meters, which basically gives us about 1.9 times 10 raised to power 17 meters as the distance. Now we need to find the speed. We know Hubble constant is given by the recession speed over the distance. So we're gonna basically, to find the speed, we got to multiply the Hubble constant with distance. The Hubble constant is 2.2 times 10 raised to minus 18, and the distance we just found out is 17. So the speed at which that body is receding would be equal to 0.42 meters per second. Is that clear, everyone? All right, Nadia, Yusra. All right, now, and Caroline, everything is clear. Zain, Shawez, Moise.
Yes, sir.
Yay. So thank God our syllabus has finished. Now we're so happy about it.